In this video, we're going to use the components from last video, the last lesson, to talk about real-world application of this notion of increasing versus decreasing to locate maximum and minimum points of a graph. So in this problem, we've got a herd of 100 deer, and they're placed on an island. The population grows initially, but eventually, due to disease and drought, the herd is driven to extinction. And the scientists that are monitoring this herd have established this particular equation, or this model, to represent the population of the deer after a certain amount of time. So you'll notice that this function notation, let's go ahead and get this spelled correctly. This function notation often tells a story. We don't have to rely on just f of x for our function notation, but if we use letters that are abbreviations for certain variables, that can be quite helpful. So p, the population, based on the time, t, that is passed. And this time unit is years. So if we want to know what the population is after 2 years' time, then we simply change the t value to 2 and evaluate the expression. That's what we're being asked to do here in Part A. A lot of times when I'm given a function like this, especially in function notation, when I'm going to be replacing the variable with a value, I'll just use parentheses everywhere that that variable exists, and then I'll come in and I'll write the number that's being evaluated. Now I'm lucky enough to have several different ink options available to me. That helps it stand out a little bit more. But in reality, this notion of parentheses, I think, is quite helpful, especially if we're dealing with negative numbers that are being used as an input. Now we can execute this by hand, or we could go to the calculator, whatever you're more comfortable with. These two components here simplified with relative ease, so we went ahead and completed that, although I just noticed a typo here. This was 20, not 2. And now 100 plus 80 minus 16 is 164. And coming from the equation, we would say p of 2 equals 164, but let's not forget we should be able to explain what it means. And of course, the 2 represented time, and 164, this is the population. This was a population calculation based on 2 years of time, so the end result is 164. We could then say, with our explanation, that after 2 years, the deer population is 164. Now, part of the instructions did say to use appropriate units, so it is worthwhile to note here that 164 is the number of deer. So now we've got a solution that contains appropriate units, and we've explained its meaning. So now the question becomes, when does the deer population reach its maximum, and what is the population at this time? This would be a really good question for my calculus students to complete without a calculator, because they have techniques to recognize where a maximum occurs. Now remember, from our discussion in the last video, we noted that a maximum occurs when the graph changes from increasing to decreasing. So visually it would look something like this. If we've got a graph that's increasing from left to right, and it switches from increasing to decreasing as we continue to move from left to right, then this location here at that transition is a maximum point. And we could evaluate that using calculus techniques. Now we're not quite there, but it is important to remember that what we're looking for is this change from an increasing graph to a decreasing graph. That's where our maximum would occur. So with our pre-calc skills, let's go ahead and use a graph to make that happen. In class during week 5, we talked a little bit about how to download and install this TI calculator. This is a software version of the handhelds that I have in the classroom. So if you practice with this at home, then you'll be well versed and ready to use the handheld calculators that I have in the classroom. If you're working at home, or if you're in the classroom, what I would ask you to do in order to graph this is press the on button until you get to this screen here, our main menu. And we can do one of two things. We can create a new document and insert a graphs page, We can do that by clicking number 1 here and then selecting Graphs page. Or if we don't plan on using this for more than just this one problem, we can just use the Scratchpad graph. We can type the letter B, or we can activate the mouse and click B on the screen. So here we have a graphs page, and now we can enter the expression. The one difference that we have with the TI Inspires is that every graphed function is a function f related to x, f dependent on x. So we can't use p, we can't use t as our variables, so we'll just have to make a mental switch of that. As we're building the function here, we're going to write 100 plus 20x squared minus x to the 4th power. So again, we have to use x's instead of t's, but that's okay. We can handle this. And there we go. Now this graph isn't particularly useful. All I see are two what appears to be vertical bars. These are actually components of a larger polynomial. We can't see its slope on this view. But since this graph isn't all that meaningful, we need to change the window. And let's just think about this for a second. I don't really know what a good window for this might be, so we could do one of two things. We can guess and check until we find an appropriate window, or we could determine the appropriate x interval, what the appropriate domain of this function is, and then ask the calculator to fit the remaining component of the window to that domain. In either case, there is a bit of guessing and checking at the beginning to determine where our x window is. There are additional techniques that we can discuss in class, but for this video I'm just going to make a guess and check. So I'm just going to guess something here. I'm going to say that the maximum population is going to occur somewhere between time 0 and time 10. I don't know for sure, but somewhere between 0 and 10 years I'd like to see if the population reaches a maximum. And the population of deer, I don't know what that'll be, but I do know that after 2 years the population is 164, and also we started with 100. So if we started with 100 and we already grew to 164, maybe I'll say that my population has to exist somewhere between 0 and, I don't know, 500 deer. Oftentimes you'll see windows described like this, graphing windows described like this, where they give you a range of x numbers and a range of y numbers. Especially in Math Excel, they like to indicate this in one form or another. And what that does is it gives us an idea of how to change our window on our calculator to see if we can find a solution. Now to adjust this window, we're here on the scratch pad, we're looking at the graph. We're going to press the menu button, choose option 4, and then option 1. So again, while we're looking at the graph, we're choosing menu, option 4, option 1. And now we can specify what our x minimum, x maximum, y minimum, and y maximum ought to be. I usually don't mess with the scale. I let the calculator determine what the scale should be automatically. Now if our x minimum is 0, and we can press the tab to jump to our x maximum, so I said somewhere between 0 and 10 years might be a good point of focus. Then I'll jump down here to y minimum being 0 and the y maximum being 500. Of course, the y value represents our population in this case. When I press OK, the graph should be recreated, and that's not too bad. At time 0, we had a population of 100, and it's a bit hard to tell the scale here because the axes land right on the edge of the graph. So let me share with you a different trick that might work. Menu 1 again. Instead of starting right at 0, let's back that up 1 unit. So we'll have an x value from -1 to 10, and then for y minimum, let's go down to, say, -50 up to 500. A rule of thumb that I like to follow is about 10% above or below the x-axis. That way we can see the axes on our graph. There we go. That's a little bit better. So now we can see the axes and we can really tell what's happening here. And also we can see our scale. We can see our scale on this graph too. Well, at least we can see our x-axis scale. This number here right next to the origin indicates our x-axis. If I were to slide this graph a little bit, we can see our y-axis scale as well. Now if I move those by sliding the mouse, then the scale gets off just a little bit. So I'll just put it back here to center. And actually, I think that number that I was pointing to was the y minimum at that point. But the scale is always reported pretty close to the origin here. Along the x-axis, we're increasing by a unit of 0.2 years. And across the y-axis, if we were to count, we've got 5 steps here to the point that's represented by the number 100. So we know that we're increasing by 20 units there. And we can see that the population of the deer did increase from 0 up to this point, and then it switched to a decreasing graph from then on. So we did encounter a maximum here as long as the function is defined at that point. And we could try to guess what that is. We could try to read the graph. We can even turn grid lines on. And that's by going into the menu, choosing View, which was number 2, and then Grid, number 2. And we can use one of these two. Problem with the grids are that on the dot matrix display of our calculators, they don't always come up even. So it might help you when estimating your result, but it doesn't ever give you a real precise answer. I'm not really a fan of the grid, so I turned mine off. But we can use the calculator to find our maximum point here. We know again that this is a maximum because we went from an increasing graph to a decreasing graph. That changed. So if we jump into the menu one more time and select option 6 to analyze the graph, and then option 3 to locate the maximum, the calculator is now prepared to find that maximum point. And what it's asking for us to do first is to identify a lower boundary. Again, we're picking a lower boundary in this window that represents a portion of the graph that's increasing. So you can see where this vertical line is being placed on the screen. This vertical line needs to be selected in a position where the graph is increasing. So anywhere from here to here would be fine. I'll be safe and place this line right here. And I'm just going to click the screen, or if you're on your handheld, you're going to press this button over here, just this center button to select. Now as we drag our mouse to the right, we need to find the upper boundary, and the upper boundary occurs where the graph switches to decreasing. So as long as I click anywhere along this graph where the graph is decreasing, then the window will be complete and the calculator will find the first maximum point within that window. And so you'll notice that as I'm dragging to the right, the maximum continuously changes. It's because it hasn't found the maximum yet. But as soon as I move my cursor to the right, in this range where the graph is now decreasing, we have a maximum that's been located. I'll go ahead and click the screen here. So the calculator recognizes this point to be a maximum at 3.16, 200. So to show my work to answer this question, I'm just going to quickly sketch this graph. And off screen I just created a set of axes, a t and a p of t, or x and y axis. And the graph looked something like this. And again, this is just a sketch of graph to support the answer that I'm about to provide, so it's not real critical that we draw this perfectly correct. I'm going to locate this maximum at the coordinate 3.16, 200. And so now we can answer the question, well, when does the population reach its maximum, and what is the population at this time? Well, with this coordinate, we have an x and y component, or t and p of t component. And as we said a little bit earlier, t represents the time, and p of t represents the population. And so I would say something like this. The maximum population of the deer is 200, and this occurred 3.16 years after being introduced to the island. And again, we found this by locating the position where the graph changed from an increasing function to a decreasing function. Now we can use this graph also to answer the next question. How long does it take for the entire herd to die off? Again, because we experienced a population that started at 100, it grew to a population of 200, and then it started to decrease. Now, the graph on our calculator, of course, decreased below the x-axis, but we know that in real life that can't happen. We can't have a negative population of deer. So what I'm interested in is the point here where the population returns to 0. Now that can easily be found by interpreting the graph as well. Oh, and by the way, we got pretty lucky with that first guess as far as our window goes. We can see enough of the graph to make it meaningful. If your first guess wasn't enough to see enough of this graph, then guess and check again. Find a new window that works. But here we're in pretty good shape. So I'm looking for this point here, and we can find that pretty easily. We'll choose Menu, Analyze Graph, so Menu 6. Now this time we'll choose option number 1 to locate a 0. I don't want to choose minimum here because this is not the minimum of the function. It's not a local minimum or absolute minimum according to the entire domain of the function. So I'm going to use 0 instead, and this will allow the calculator to find the location of the 0, or where the graph touches the x-axis, where the y value is 0. And very similar to the last tool that we used, we need to provide a lower boundary and an upper boundary. So I'm going to slide this cursor somewhere to the left, close to this point of intersection, but just to the left of it. We don't have to be real critical here about the location. And then we'll just slide our cursor a little bit further to the right. And we see a solution here. We see a coordinate, 4.91, comma, now 5.82 e negative 11 means, that's scientific notation, 5.82 times 10 to the negative 11th power. That's like 11 zeros in front of a 5. That's awfully close to 0, so I'm going to call that good enough. So this location was 4.91, comma 0, and we can now answer question part C. And we could say something like this, that the herd will die off after 4.91 years, and this occurs when P of t equals 0. So essentially we're saying that P evaluated at 4.19 equals 0, if we're using function notation. Now for the last question in this video, we'll go ahead and answer part D here. At what time is the deer population equal to 150? Well, again, this is our way of asking, when does P of t equal 150? Or, since P of t represents a y variable, we can think, when does y equal 150? Or, since we're using a TI calculator, when does f of x equal 150? All three of these claims mean the same thing as long as we're using the same units. So if I jump into the calculator here, I can add another equation that's going to create a horizontal line here at 150. And then we can find where that equation intersects our population equation, and we'll know exactly when the population reaches 150. And I think that's going to happen twice. Once as the population increases past 150, and then again after it falls down below 150. So let's see if we can locate that. Now we need to pull up the function bar at the top of this screen, and we do so by pressing the Tab key if it's not visible. Now my calculator for some reason does this when I'm recording videos, and it sometimes flashes. Yours shouldn't do that. So let me try this again. We'll go back to the graphs page. Okay, I think I got it to stop. So again, here's the function f of x. This has got a number 2 next to it because it's the second function. We're just going to type f of x equals 150 and press enter. We'll take a look at that graph. So here's our target line. Here's where the target of 150 deer is set. We'll just ask the calculator to find the intersection of those two lines. So we're going to go into the menu one more time, choose Analyze Graph, and this time, instead of choosing 0, and instead of choosing maximum or minimum, we're going to select the option Intersection. Now here's where our boundaries are going to be really important. If we pick a lower boundary to the left of this intersection and slide to the right, the calculator will find that intersection. And it would be nice if we can just keep sliding to the right and find the other intersections, but evidently the calculator just doesn't operate that way. It can only find one at a time. So I'll go ahead and close the upper boundary here, and then I'll try that pattern again. Menu 6, then number 4, menu 6, 4, and I'll try this again. Again, I'm going to provide a lower boundary, so I'll click somewhere to the left of that intersection. This is getting a little bit messy with all of those points, and I think I got it there. Let me move this guy out of the way. There we go. Yep, I've got him. So at time 1.71 and at 4.13, the population ended up reaching 150. And so we can answer that with coordinates like this and then a brief description. And we've got a pretty good answer for this particular problem. Now here's a challenge for you as we finish this out. Is there a way for you to find the times when the deer population reaches 150 without using a graph? I wonder if you recall how to do this from your old Algebra 2 days. Here's a hint. 150 was our population, and the equation 100 plus 20t squared minus t to the fourth represented our population growth over time. How could you use this to find the time 1.71 and 4.13? If you figure it out, let me know in class when we see each other next. I know this video was quite lengthy, but thank you for watching, and hopefully you gained something from it, especially with the practice with the calculator. If you've got further questions, please let me know. Thanks for watching.